Hey there, deep divers. Ever stop to think about uh, the magic that lets you effortlessly switch between like browsing the web, streaming music, and editing documents on your computer?
Hmm.
Well, today's deep dive is going to pull back the curtain on that magic. We're diving into the world of operating systems, the
Ah,
unsung heroes that make all that digital juggling possible.
and you might be surprised to learn just how much impact they have on everything you do with your computer, even if you've never written a line of code in your life.
You're telling me. For this deep dive, we've got some fascinating university lecture notes
Oh, cool.
and even real-world code examples to help us unpack this intricate world.
Neat.
We'll be exploring what operating systems do, how they work internally, and the different types that exist.
Oh,
So, ready to unlock the secrets of the digital engine room?
absolutely. A good starting point might be understanding what exactly an operating system is.
Okay,
It's not just a bunch of lines of code.
okay, enlighten me. I'm all ears.
Well, think of it like a government for your computer. Just like a government manages resources and provides services to its citizens, an operating system manages your computer's resources like the processor, memory, and storage, while providing essential services that allow applications to run smoothly.
So, if the operating system is the government, are applications like the citizens?
Yes,
Do they rely on those government services to function?
precisely. They need those services to get anything done. And a well-designed operating system ensures that all your applications have access to what they need without stepping on each other's toes or causing system crashes. That's why understanding operating systems can be beneficial even if you're not a programmer. It's about understanding how your digital world functions.
That's a great analogy. Now, our source material mentions different software layers. Can you break those down for us?
Of course, it's helpful to picture it like a layer cake. At the top, you have your application software, the programs you interact with directly, like web browsers, games, or that spreadsheet you're using to track your fantasy football league.
Ah, yes. Can't forget about fantasy football.
Exactly. Then comes the system software layer, which acts as the bridge between those applications and the hardware of your computer. This is where the operating system lives, working tirelessly behind the scenes.
So the operating system is like the middle management, making sure everything runs smoothly between the top-level applications and the hardware.
You got it. And within that middle management, we have libraries, which are like pre-built toolkits for programmers, and the kernel, which is the heart of the operating system. It's responsible for the most critical tasks like managing memory and communicating with hardware devices.
Libraries sound interesting. Are those like pre-written code snippets that programmers can use to build their applications faster? Sort of like using pre-made Lego blocks?
That's a great way to put it. Libraries help developers avoid reinventing the wheel for common functions, which speeds up development and makes software more reliable. It's all about efficiency.
And that brings us to something called system calls, which I've seen mentioned a few times in our sources. What are those exactly?
System calls are how applications request services from the kernel. Think of it like submitting a request to the government for a permit or a license. The application needs the kernel's permission to access certain resources or perform certain actions.
So it's a way for applications to politely ask the operating system for permission to do something potentially sensitive.
Exactly. It's a crucial mechanism for maintaining security and stability.
This is where things get really interesting. Our sources include some Hello World program examples, which show how different coding approaches lead to different interactions with the operating system. What's going on there?
These examples are fascinating because they illustrate the trade-offs developers face. One example uses standard library functions to print Hello World, while another uses a direct system call. While both achieve the same result on the surface, they highlight the behind-the-scenes differences.
So even something as simple as printing Hello World involves these choices.
Absolutely. Libraries can simplify development but might add a bit of overhead, whereas direct system calls offer more control but require more careful coding. It's like choosing between taking the scenic route or the expressway. Both get you to your destination, but one might be faster depending on traffic conditions.
I see. It's all about picking the right tool for the job.
Exactly. Developers need to consider factors like performance and security when making these decisions.
Now, let's shift gears and talk about concurrency and parallelism, two concepts that seem to go hand in hand.
They're often used interchangeably, but there's a subtle yet important distinction. Imagine a juggler keeping multiple balls in the air. The juggler isn't necessarily handling all the balls at the same time, but they're making progress on each by swiftly switching between them. That's concurrency.
Okay, that's a great visual. So concurrency is about managing multiple tasks, even if they're not happening truly simultaneously.
Precisely. Now imagine multiple jugglers, each managing their own set of balls simultaneously. That's parallelism. It requires multiple processing cores, each capable of tackling a task independently.
So concurrency is like a single chef managing multiple dishes on a stovetop, while parallelism is like having a team of chefs, each working on a different dish in their own kitchen.
A perfect analogy, and both are crucial in modern computing. Concurrency makes multitasking possible even on a single-core processor, while parallelism unleashes the full power of multi-core systems for demanding tasks.
It's incredible how much complexity is hidden beneath the surface of something we take for granted every day.
And we've only just begun to scratch the surface. Next, we'll dive into the different types of operating systems out there.
Okay.
From the workhorses of personal computers to the specialized systems powering everything from smartphones to spacecraft.
Sounds fascinating. Stay tuned, deep divers, as we continue our exploration of the intricate world of operating systems. Welcome back, deep divers. Last time, we laid the foundation, exploring what operating systems are, their different types, and some key design principles. We even got a glimpse into that fascinating world of Hello World programs and how they interact with the operating system at different levels.
It really is amazing how much complexity is hidden beneath the surface of even the simplest actions on our computers. Every click, every keystroke, every file you open, it triggers a cascade of events involving the operating system.
Like there's this whole secret world operating behind the scenes, making our digital lives possible.
Exactly. And today we're going to journey through time to uncover how operating systems have evolved over the decades.
Ooh.
From their humble beginnings to the sophisticated systems we rely on today.
Okay, history lesson time. I'm ready to hop into our time machine. Where do we begin?
Our journey starts in the early days of computing, when computers were behemoths, filled with vacuum tubes and required manual operation. Imagine having to physically flip switches and plug cables for every single program you wanted to run.
Wow, that sounds incredibly tedious and time-consuming.
Yeah.
I can't imagine having to do that every time I wanted to check my email.
It was a far cry from the user-friendly experience we have today.
Yeah.
But even back then, those pioneers were laying the groundwork for the future of computing. The second generation of computers saw the introduction of transistors, which made computers smaller and more reliable. This paved the way for batch processing systems, where multiple programs could be submitted as a batch and processed sequentially without direct user intervention.
So that's when the idea of automating tasks started to emerge. It's still not quite the interactive experience we have today, but it's a definite step in the right direction.
Absolutely. Batch processing was a major breakthrough in terms of efficiency. However, it still lacked the interactivity and responsiveness we've come to expect. That's where the third generation comes in the era of multi-programming and time-sharing systems. These systems allowed multiple programs to reside in memory simultaneously and share the processor's time, creating the illusion of multitasking.
Ah, so this is when computers started to become more versatile and productive.
Precisely. The third generation also saw the development of concepts like spooling, which allowed print jobs to be queued and processed in the background, further enhancing efficiency. And this brings us to the fourth generation, marked by the rise of personal computers with those familiar graphical interfaces. Operating systems like MS-DOS, Windows, macOS, and Unix became household names, ushering in a new era of computing for everyone.
This is when computers really started to enter our homes and workplaces, right? Suddenly, they weren't just for scientists and engineers anymore. They became tools for creativity, communication, and entertainment.
Exactly. And the evolution hasn't stopped there. Since the year 2000, we've seen the rise of virtualization technologies like virtual machines and containers. These technologies allow multiple operating systems to run simultaneously on a single physical machine.
So it's like having multiple computers within a single computer. That's mind-blowing. Our sources mention some examples of this like OpenStack, Docker, Kubernetes, and Podman. What are those exactly?
Those are all powerful tools used in modern data centers and cloud computing environments. They play a crucial role in managing the complex applications and services we use every day, from online banking to streaming movies.
It's incredible how far operating systems have come from those early days of flipping switches and plugging cables.
It truly is a testament to human ingenuity and our relentless pursuit of technological advancement. But the journey isn't over. Operating systems continue to evolve at a rapid pace, driven by the increasing demands of artificial intelligence, big data, and the Internet of Things.
Now, let's shift gears and dive back into those system calls we discussed earlier. They're like requests from applications to the operating system kernel, right? Can we explore how they actually work in more detail?
Of course, the process of entering the operating system kernel to handle a system call is quite fascinating. It can happen in several ways, depending on the nature of the request and the specific circumstances. Sometimes the application itself issues a system call instruction. Other times, a software interrupt triggered by an exception or a hardware interrupt generated by a device will prompt the kernel to step in.
So it's like different ways of getting the kernel's attention depending on what needs to be done.
Exactly. It's like a sophisticated communication system where applications can signal their needs to the operating system. Once the kernel's notified, it switches the processor from user mode to system mode, granting it access to privileged instructions and resources.
Hold on, user mode and system mode, what are those?
These are two distinct operating states of a processor. User mode is the restricted environment where applications run, with limited access to system resources. This is essential for security, as it prevents rogue applications from interfering with critical system operations. System mode, on the other hand, is the privileged mode where the operating system kernel operates with full access to the hardware.
Ah, so it's like having different levels of security clearance within the computer. Applications are kept on a tight leash in user mode to prevent them from causing havoc, while the kernel has full authority to manage everything.
That's a great analogy. This separation of privilege is a cornerstone of operating system design. By carefully controlling access to resources, the operating system ensures stability and prevents malicious or faulty applications from bringing down the entire system.
This is starting to make a lot more sense.
So, whenever an application needs to do something that requires privileged access, like reading from the hard drive or sending data over the network, it has to make a system call. Precisely. The system call acts as a controlled gateway into the kernel, allowing the operating system to carefully manage these sensitive operations. It's like going through customs at an airport. You need the proper authorization to proceed.
That makes perfect sense.
Yeah.
But our source material mentions that system calls can be quite expensive in terms of performance. Why is that?
Well, switching between user mode and system mode involves a certain amount of overhead. The processor needs to save its current state, switch to the kernel's context, execute the requested operation, and then switch back to user mode, restoring the previous state.
So it's like taking a detour every time you need something from the government instead of just grabbing it yourself. There's a cost associated with that extra step.
That's a good way to put it. Efficient programs try to minimize the number of system calls they make to reduce this overhead. It's all about finding the right balance between security and performance.
Speaking of efficiency, I remember we discussed libraries earlier. How do they fit into the picture of system calls?
Libraries are like helpful assistants for developers, often providing higher-level functions that encapsulate multiple system calls, making it easier to perform common tasks without writing a ton of code. For example, a library function to read a file might actually involve several system calls behind the scenes, like opening the file, reading the data, and closing the file.
So libraries act as intermediaries, simplifying things for applications while still relying on the operating system's core functions.
Exactly. They provide a more convenient and often more efficient way to interact with the operating system, streamlining the development process.
Now let's revisit modular architectures and kernel modules. Can you tell us more about those?
Kernel modules are like building blocks for operating systems, particularly those like Linux, which are renowned for their flexibility and customizability. They're essentially code snippets that can be loaded and unloaded dynamically into the kernel, allowing the operating system to adapt to different hardware and software environments on the fly.
So they're like plugins for the operating system, adding new functionality as needed.
That's a great way to think about it. This modular design allows developers to add new features or support for new hardware without having to rebuild the entire kernel, which would be a time-consuming and complex process.
That sounds incredibly useful. It's like being able to upgrade your car by simply adding new components without having to rebuild the entire engine. Can you give us some specific examples of what kernel modules can do?
Kernel modules can implement a wide range of functionalities, from device drivers that allow your operating system to communicate with your printer or graphics card, to file systems that dictate how data is stored and retrieved on your hard drive. They can even implement network protocols, enabling your computer to connect to the internet and communicate with other devices.
So it's really all about extending the capabilities of the operating system and tailoring it to specific needs.
Exactly. And that's a key advantage of modular architectures. They allow operating systems to be incredibly versatile, adapting to a wide range of applications and environments.
Our sources include a code example of a Hello World program implemented as a kernel module. What's the significance of that example?
That example demonstrates how kernel modules can be used to extend the operating system at a very fundamental level. By writing code that runs directly within the kernel, developers can tap into the core functionality of the system and create powerful new capabilities.
But that sounds like it could be potentially dangerous, right? What's to stop a rogue kernel module from crashing the entire system?
You raise a valid point. Kernel modules operate with high privileges, so any errors or malicious code could have serious consequences. That's why operating systems typically have mechanisms in place to verify the integrity and security of kernel modules before they are loaded.
So it's a powerful tool that needs to be used responsibly and with great care.
Yeah.
It's fascinating how operating systems balance this need for flexibility and extensibility with the critical need for stability and security.
It's a constant balancing act, and one that operating system designers are constantly striving to perfect. As technology advances and the demands on our computers increase, finding innovative ways to maintain this balance will become even more crucial.
Well, we've covered a lot of ground in this part of our deep dive. We've journeyed through the history of operating systems, explored the intricacies of system calls and kernel modules, and even touched upon that vital distinction between user mode and system mode. I'm starting to appreciate just how much thought and ingenuity goes into the design of these systems.
It's truly a fascinating field, and we've only just scratched the surface. In the final part of our deep dive, we'll delve into that fascinating world of concurrency and parallelism, explore the importance of separating mechanisms from policies, and leave you with some thought-provoking questions about the future of operating systems.
I can't wait to continue our exploration. Stay tuned, deep divers, for the final installment of our operating system adventure.
Welcome back, deep divers. We've journeyed through the history of operating systems, delved into their inner workings, and uncovered some of their key design principles.
Right.
Now let's turn our attention to one of the most fundamental principles in operating system design,
Okay.
the separation of mechanisms and policies.
Okay, remind me again why this separation is so important. I remember we touched on it briefly in the previous parts, but I'd love to hear more about its real-world implications.
It's all about flexibility and adaptability. Think of it this way. Imagine if every time a government wanted to change a law, they had to rewrite the entire legal system.
Yeah.
It would be incredibly inefficient and inflexible.
That's a great point. It makes much more sense to have a system where you can modify the laws without having to tinker with the underlying machinery of the legal system itself.
Yeah.
Is that essentially what the separation achieves in operating systems?
Exactly. It allows system administrators to easily customize behavior without modifying the core functionality. It's like having a set of building blocks that can be rearranged to create different structures without having to reinvent the blocks themselves.
Can you give me a concrete example to help illustrate this?
Sure. Let's consider access control in a file system. The mechanism might involve checking permissions associated with each file and user. Think of it like a lock on a door. The policy, however, determines what those permissions are. Who has the key to unlock the door, so to speak? It's the set of rules that dictates who has access to what.
So the mechanism is like the lock on a door, and the policy is like the set of rules determining who has the key. That's a great analogy. I can see how separating those two aspects would make the system much more adaptable. You could change the access control policies without having to modify the underlying locking mechanism itself.
Precisely. You could grant or revoke access to different users or groups without rewriting the code that handles the actual locking and unlocking of the files. This principle applies to many aspects of operating system design, from memory management to networking to security.
It sounds like this separation of mechanisms and policies is crucial for creating systems that can evolve and adapt to changing needs. It's all about future-proofing the design, isn't it?
Absolutely. By designing systems with this principle in mind, we create systems that are not only robust and efficient, but also adaptable to unforeseen challenges and opportunities. It's a testament to the foresight of the early pioneers of operating system design.
Now, before we wrap up our deep dive, I want to circle back to the concepts of concurrency and parallelism. We touched upon them earlier, but I think it's worth highlighting their significance in shaping the way we use computers today.
You're right. They're essential concepts for understanding how modern operating systems handle the increasingly complex tasks we throw at them. Remember our juggler analogy. Concurrency is about making progress on multiple tasks by rapidly switching between them, even if they're not actually executing simultaneously.
Right, like a single chef managing multiple dishes on a stovetop, making sure each one is cooking properly, even though they can only attend to one at a time. And parallelism is like having a team of chefs, each dedicated to preparing a different dish simultaneously, right?
Perfect analogy. And both approaches are crucial in modern computing. Concurrency allows our computers to seemingly perform multiple tasks at once, even on a single core processor. It's what makes it possible for you to browse the web while listening to music and having a video call all at the same time.
It's like our computers have become master multitaskers thanks to these concepts.
Exactly. And parallelism takes this to the next level, enabling true simultaneous execution of multiple tasks by harnessing the power of multi-core processors. This is what allows us to edit high-definition videos, run complex simulations, and play graphics-intensive games without our computers breaking a sweat.
It's amazing how these concepts have revolutionized the way we interact with technology, making our computers more powerful, versatile, and responsive than ever before. It makes me wonder what's next for operating systems. What new innovations are on the horizon?
That's the beauty of it all. The world of operating systems is constantly evolving. As technology continues to advance, we can expect to see even more innovative approaches to managing resources, enhancing security, and improving user experience. The rise of cloud computing, the Internet of Things, and artificial intelligence are all presenting new challenges and opportunities for operating system designers.
It's an exciting time to be witnessing these developments, and I'm eager to see how operating systems continue to shape our digital world. Well, we've covered an incredible amount of ground in this deep dive into the world of operating systems. From their historical evolution to their intricate inner workings, we've explored the key concepts and principles that make these systems so fascinating and essential.
We've seen how they manage resources, handle system calls, adapt to different environments through kernel modules, and ensure stability through the separation of mechanisms and policies. It's been a journey through the engine room of the digital world, and hopefully you've gained a deeper appreciation for the complexity and ingenuity behind the technology we use every day.
Absolutely. This deep dive has been an eye-opening experience, and I encourage all our listeners to explore the source material further and continue pondering the ever-evolving world of operating systems. As you interact with your computers and devices, take a moment to appreciate that intricate dance of hardware and software orchestrated by these amazing systems.
And as technology continues its relentless march forward, keep those questions in mind. How will operating systems evolve to meet the demands of the future? What new challenges and opportunities await? The answers lie in the hands of the brilliant minds who continue to push the boundaries of what's possible.
Until next time, deep divers, keep exploring and stay curious.